So in question 51, we've got a projectile. I don't know, let's suppose it's down here at some initial level. So initially it's down here. And I'll call this I'll suppose it starts off at the reference level. And that can be at 0 meters. And so the initial gravitational potential energy of this ball I'll call 0. And then what happens is this thing is shot off into the air with an initial speed of 18 meters per second. So it goes flying off up to here. And when it reaches a height h, so if this is a height h, it just comes to rest and then starts falling back down again. So it gets shot off into the air, eventually reaches the maximum height, and then goes back down again. So what the question wants us to find out is, what is this maximum height? So up here at this maximum height, it's going to have some gravitational potential energy of what I'll call UGF, and that's going to be equal to the mass of the thing. So this thing has a mass of m times g times that h. And because it's at its highest point, it's just about to turn around and start falling back down again. So it's going to have, its speed is going to be 0. And we're going to assume that there's no air resistance acting on this ball. So in part A then, no air resistance. And that sort of implies that only gravity does work on the ball. Sorry, not necessarily on the ball, on the projectile. And I'll say during its flight. Actually, during its upward journey. And what that means then is that the net work being done on this ball, so work net, is going to be equal to just the work being done by gravity, which, as always, is equal to the negative of the change in the object's gravitational potential energy. And since that is equal to the total work being done on it, that is, by the work kinetic energy theorem, equal to the change in its kinetic energy. So if we now write in what the change in the gravitational potential energy is, that's going to be this UGF. So we're going to have UGF minus UGI. And the change in the kinetic energy is just the final kinetic energy minus the initial kinetic energy. So the final kinetic energy here is going to be 0 because it finishes up with 0 speed. And the initial kinetic energy is just going to be a half m times v I squared. And now we know what UGF is. That's going to be mgh. It's going to have minus mgh is equal to minus a half mvi squared. And I suppose we should just note that m is in fact the mass of the projectile. So there's absolutely no confusion. But in any case, whatever that is, it doesn't particularly seem to matter in this case because both sides of this equation have a common factor of m, of the mass, so we can just cancel that out. And then we can easily solve for the height that the projectile rises to. So all we need to do that, see that, is just divide both sides by g. And we can also cancel out a minus sign there as well. So we then find that the height to which the ball rises is going to be equal to its initial speed squared divided by 2 times g. And if we plug numbers in, what we find in that case is that the height that it rises to is going to be approximately 16.5 meters. So that's part A. Now in part B, we assume that the projectile rises to a maximum height of only 11.8 meters. So in that case, we're going to have h is equal to 11.8 meters. But again, the initial speed will still assume be 18 meters per second. And now we must have, since this height is less than that one, there must be another force doing work on the ball, on the projectile in this case. So the other force, besides gravity, that could do work on that projectile is just air resistance. So in this case, now air resistance does work. It does work on projectile. And that means that the net work that's being done on this projectile, the net work is then going to be equal to the sum of the work getting done by gravity plus the work being done by air resistance. So I'm going to call the work done by air resistance WF. And since that is now, again, the net force, that is going to be equal to the change in its kinetic energy. Now, again, we can write out what the work done by gravity is. It's going to be equal to the negative of the change in the gravitational potential energy. And the work that gets done by air resistance is just going to be equal to the average force that is applied by the air resistance times the distance over which that force is acting. So presumably, the air resistance force will act over the entire distance that the ball is ascending for. So that's going to have to be h. And I've stuffed up the signs here because the air resistance force is acting in the opposite direction to the way that the ball is travelling. So it's going to be doing negative work on that projectile. So we need to put a minus sign there to account for that. And then this is going to be equal to, once again, the change in kinetic energy. Now its final kinetic energy, when it gets to the top of its flight, is just going to be 0, and then the initial kinetic energy is just what it was before. And then if we plug in what the gravitational potential energies were, we find that this is going to be minus mg h. And actually, let's call the height to which it rises h2. So I'm going to change that 11.8 into h2 so we don't get confused with what it was up there. And what do we want to solve for? We want to solve for this average force. So if we just add mgh2 to both sides, then we find that we get to this. So the mgh2's cancel on that side, but we have plus mgh2 on the right-hand side. And now to solve for the average force, we just need to divide both sides of this equation by minus h2. So we're left with the average force is equal to minus 1 on h2 times by mg h2 minus a half mvi squared. And so now, if we just take the numbers that we're given and plug those into the calculator, we get that this is minus 1 divided by 11.8. So what's the mass of this ball? The mass is 0.75. So let's write that down up here. Mass is equal to 0.75 kilos. So we have and then take away this term, and V1 squared was 18 squared, so I find that the average net force applied by air resistance was 2.95 newtons.